These are notes on section 13.1. Right, so on page 848, we're now doing vector functions and space curves. Okay, so a function r of t, it's a vector. There's actually three parts to it if it's a 3D type of function. You see f of t, g of t, h of t. These are all functions of t normally because it stands for time. Okay, so your position vector, r of t, can be thought of as f of t I plus g of t j plus h of t k. So as time goes by, x changes, y changes, and z changes. So we're calling it one function, one position function, r of t, but when you open up, there's three functions involved in it, x, y, and z. Okay, so here's an example. R of t is t cubed ln 3 minus t squared of t. Okay, we're calling it one function, a function, but there are three functions associated. This is the x is t cubed, y is ln 3 minus t, and z is radical t. So when we talk about limits and continuity, you're talking about three functions at once. Okay, so for instance, to find the limit of the whole thing, you simply take the limit of each component, the x, y, and z components, provided that they all exist. Okay, all right, this will generate nice space curves. Most of the time, we won't be drawing them. You can have software that draws these things. So as time goes by, here's your position function, r of t. Okay, so there's x is a function of t, y is a function of t, z is a function of t. Put them all together, and it traces out some three-dimensional curve, perhaps. Right, and so you get some nice shapes. There's a space curve in red. Don't look at the cylinder, but just the red, figure 2. Okay, and just to see the nice things you can generate on a computer, if I can get this thing focused. Okay, so here's some nice pictures that you can get. Again, you don't have to draw these if you don't want to. There are traces, as you can see here, A, B, and C, and then A, B, and C are three-dimensional graphs, and then D, E, and F looks like they're traces in coordinate planes. And you get some interesting pictures like this, which most of the time you won't have to draw. You'll have to draw very little in this class. All right, so here are some of the problems on page 853, 13.1, for those of you that don't have the book and aren't getting it. Get this thing focused there. All right. And then page 854. Okay, so there are some sketches here that you have to do. I don't make you do that many sketches, but just a few. And I don't think you have to do those because they involve sketches. And I think we have to go up to 27, and 27 is the last one. Okay. Okay, so question number 1 asks for the domain of the function, number 1. So you have three functions in one. R of t is ln t squared plus 1. That's the x component. T over whatever, that's the y component, and 2 to the t as the z component. So if you're going to talk about the domain, the t value has to be allowed for x, y, and z. Okay? So once you get a situation which is not allowed, that makes the whole function not allowed. So for instance, you cannot take the natural log of a negative number. So any t which makes this expression negative is out of the question. It doesn't matter whether this is defined or this is defined. Once you get something which is undefined for one of them, then that has to be thrown out of the domain. So you want the t values which make sense for all three of them. All right, so from the x component, we know that we can only take the natural log of positive stuff. So t plus 1 is greater than 0, which means t is greater than -1. From y, well, square root of 9 minus t squared, that has to be greater than 0. If I add t squared, 9 is greater than t squared. If you think of the graph of the parabola t squared, that's going to happen when t is between -3 and 3. For z, 2 to the t, there's no limitations on t. There's no limits for t. So I have to combine this and this. In other words, t has to be between -3 and 3 inclusive, but it also has to be greater than -1. So putting it all together, my domain is parenthesis -1, comma 3 bracket, okay, which is a combination of this and this. Okay, question 3 asks for the limit of this function. Again, it's basically 3 and 1. So the language we're saying is that we're taking the limit of the function, but there are 3 functions involved. You open it up and there are 3 functions, the x part, the y part, and the z part. Okay, so the limit as t approaches 0 for the x component, just plug it in. E to the 0 is 1. Z is also easy, so plug in 0. Cosine of 0 is 1. Okay, y is a little bit of work. So I take the limit as t approaches 0. Let me break this up into t over sine of t quantity squared. And you might recall from Calc 1 that this limit is 1. So I'm going to have 1 squared, which comes out to be 1. You could also do L'Hopital's rule. Okay, so my final answer is 1, 1, 1. This limit is 1. This limit is 1. This limit is 1. Okay, 7. R of t is sine t. T, you're asked to make some kind of graph. It's 2 dimensions, so if it's 2 dimensions, there shouldn't be any issue. Okay, this one involves trig. So I just decided to go from -2 pi to 2 pi. So plug in -2 pi, I get 0. -3 pi over 2 is 1. Negative pi is 0. Negative pi over 2 is -1. 0 is 0. Pi over 2 is 1. Pi is 0. 3 pi over 2 is -1. 2 pi is 0. So I'm just plugging right in here. And for y, the function is just t, so I just match it. -2 pi, -3 pi over 2, negative pi all the way down to 2 pi. It just matches. Okay, and then if you plot, you get a graph that looks sort of like this, which kind of looks like your sine curve, or I guess is negative sine, tilted 90 degrees. So that's what I have there. Okay, 13, graph in 3D. R of t is t squared, t to the 4th, t to the 6th. Okay, so I just make a table. 0, I did plus or minus 1. Notice because the exponents are 2, 4, and 6. If you put 1 or -1, you get the same thing, and 2 and -2, you get the same thing. So 0 gives me the origin. Plus or minus 1 gives me 1, 1, 1. Plus or minus 2 gives me 2 squared, which is 4. 2 to the 4th is 16. 2 to the 6th is 64. So z grows the fastest. Y is the next fastest, and then x doesn't grow very much at all. So very crudely, here's a first octant view: 0, 0, 0, 1, 1, 1, 4, 16, 64. So something that looks like this. Okay, 19. Asks for vector equation and parametric equations for the line segment joining P and Q. So from P, 0, -1, 1 to 1/2, 1/3, 1/4. Okay. We have a formula for that. You can write this on your cheat sheet. R of t is 1 minus t R0 plus t R1. What are R0 and R1? They're simply the original points and the ending points written as a vector. So instead of the point 0, -1, 1, which means parentheses, just change it to vector 0, -1, 1. And likewise, 1/2, 1/3, 1/4, 1/2, 1/3, 1/4, except instead of putting parentheses, make it as a bracket. And 1 minus t here, t here. Okay, then you just clean it up. So 1 minus t times 0 is 0. 1 minus t times -1 is t minus 1. 1 minus t times 1 is 1 minus t. And then t times 1/2, 1/3, 1/4. Put them together, 0 plus half t. T minus 1 plus 1/3 t becomes 4/3 t minus 1. And then 1 minus t plus 1/4 t becomes 1 minus 3/4 t. So that's my position vector R. Okay, so x equals 1/2 t, y equals 4/3 t minus 1, z equals -3/4 t plus 1, and t goes from 0 to 1. Okay, and by the way, quick double check, what happens when you plug in 0? Plug in 0, you get 0, -1, 1. And what happens when you plug in 1? You get 1/2. 4/3 minus 1 is 1/3. And negative 3/4 plus 1 is 1/4. So it definitely works. Okay, and finally 27, we're just asked to verify and get this thing focused. Right, so they just give me this and you don't have to sketch it. But show that this satisfies z squared equals x squared plus y squared. No big deal. Z squared is t squared. X squared is t squared cosine squared t. Y squared is t squared sine squared t. Factor out a t squared cosine squared t plus sine squared t, which of course is 1. So yes, indeed, you get t squared either way. Right? All right, so these are notes on 13.1.